radio and open new opportunities also. So take it away. Thank you.
Yes, thank you. I hope you can see everything all right and hear me fine. I totally
Yes,
have no
all fine.
view of the Teams window anymore, so just shout at me when something's going wrong. Yeah, so thank you to the organizers for allowing me to tell you a bit about radio transients, and thank you for allowing me to give this presentation online. And also thank you for everyone there for hanging in there to really the final talk of this conference. Yeah, so bridging the spectrum, going from optical to radio. So first I want to sort of hopefully reiterate why radio is important, even to everyone working on optical transients. So some of the transients we work on, we've heard a lot of them already, but tidal disruption events, fast blue optical transients, and afterglows of supernovae and gamma ray bursts. So a general picture is that in the radio, we probe the ejected material during a transient or an explosion, and how this interacted material, the ejected material interacts with the surroundings. So you can see a picture here, hopefully you can see my mouse, where a massive star collapses and we get a supernova explosion, and sometimes we can also observe the gamma ray burst. And all the material that is expelled during this explosion will start to interact with the surrounding medium here, and this is the afterglow that we can see in the radio. And to tell a bit more about the science that we can actually get out of that, I want to focus on this system that I worked on, which is recurrent nova, RS Ophiuchi, which is nice because then I can also show an optical light curve, which I don't have many of those. So that's a white dwarf that is in a binary with a red giant, and the white dwarf accretes from this red giant, and roughly every 15 years enough material heaps up on the surface of the white dwarf that you get a thermonuclear explosion on the surface of the white dwarf. And you can see this in a very drastic optical brightening, but you can also see this in the radio. So these are some of the radio light curves that we obtained from the latest outburst of RS Ophiuchi. And without going into too much detail, we have a LOFAR and meerkat observations. So that's really low radio frequencies. So LOFAR is 150 megahertz or 2-meter wavelength. And you can see that we obtain flux density measurements from a few days after the outburst to roughly 200 days after the start of the outburst. And what we can do with this radio data is we can perform several fits that you see in these two panels here, and this really allows us to say something about the emission components at play. And for this particular outburst, we could quite confidently say that there are at least 2 synchrotron emitting components, which really helps us interpreting the structure and environment around this source. Another thing we can do, as I already mentioned with the radio, we really probe this interaction of the ejected material with the surrounding medium. And for this particular system, the density of the surrounding medium is really determined by the red giant mass loss rate. So studying the radio light curve, we can get a really good estimate of the red giant mass loss rate. So hopefully I've made clear that radio observations are important, even from some of these transients that we usually think of as optical transients. And of course, we're facing sort of the same problem that we've been talking about all week, is how will we decide which transients to follow up, in this case in the radio, if we're starting to discover thousands of them. Of course, we're already thinking about this. We select on some of the optical properties. Usually we go for the brightest ones, of course, but I think we should really have a think about how to revise these selection criteria in the LSST era. And I also want to point out that follow-up can be time critical. So often we may think of the radio as coming later, being delayed compared to the optical light curves, but in some cases, the interesting science is really in the early time. So here's a light curve that shows the afterglow of a particular gamma ray burst, where they really got radio data in the first few hours after the gamma ray burst was detected. And using these data points, they were really able to model the GRB reverse shock in detail for the first time. So we do sometimes really need time critical follow-up. And another point I want to make is that we have to think about which transients to follow, but also about how to follow them up. Because which radio facilities will we actually use to perform this follow-up? Well, hopefully, if you think of radio telescopes, especially in the southern hemisphere in the near future, you think of the SKA, the Square Kilometre Array, which will be consist of 2 parts in South Africa and Australia. And it will be an amazing instrument. It will have incredible sensitivity and resolution. That's sort of a great thing about radio instruments. We can make them incredibly sensitive, high resolution, high time resolution, high frequency resolution. But that also means that it will be, a lot of people will want to use it. So it will be difficult to do high cadence follow-up or triggered observations or long-term monitoring of the transient sources that we're interested in. So to give an example of why these two, why high cadence monitoring and long-term monitoring are interesting, especially looking at it from a transient perspective. So for example, in the radio, we want to look for coherent radio emissions, so sort of these fast radio burst-like signatures that come from gamma ray bursts or from binary neutron star mergers. And for that, we want to look as close as possible to the event, to the gamma ray burst or to the gravitational wave event. So we really want to want triggered observations, which will be difficult to do with the SKA. Well, it won't be difficult, but you will have to make a really good case of why you want to override everything to look at your particular source. For more information about this specific topic, also take a look at Rana Starling's poster, who has made an overview of the work that we've been doing on rapid radio observations of gamma ray bursts. And a case why we want to do long-term monitoring, well, we've seen light curves that are not only high cadence, but also they extend over hundreds of days in time since discovery. And an example that I show here shows the follow-up of a tidal disruption event, where these color triangles show upper limits in the radio. So over the first 100 days, we don't really see any radio signature. But after 100 days, we see this very interesting radio flare, which indicates some sort of state transition of that system. So it can be very, it can yield very interesting science to actually look at certain transients for a long time. Yeah, so coming back to this, which radio facilities will we use to perform the follow-up? So I'm only a final year PhD student, so I'm not really in the business of thinking of new radio facilities, but there's this really interesting paper by Rob Vander and collaborators that has some discussion about filling this radio transient gap, and where they make the case for a radio transient monitoring array in the southern hemisphere. And some of the ideas include repurposing SCAP, not XAP, or ETCA, which are two radio telescopes in Australia, or the African Millimeter Telescope, which has been suggested maybe as to be part of the EVN, so these very high resolution images of black holes, but could also potentially be interesting in terms of transient follow-up. So another thing I want to quickly switch over to is optical follow-up of radio transients. So basically the other way around. So it's been very interesting for me to hear about all these fantastic brokers that have been discussed all week. Because in the radio, especially the type of radio I do, so image domain radio transients, where we're not quite there yet. So we're not finding as many that we need these very highly sophisticated brokers with interesting classification algorithms. But we do start to find some interesting sources. So this is a source that I work on. It shows bright minute duration radio flares, which may be periodic, may not be periodic. We're still about to find out. And they're highly linearly polarized. And this sort of indicates that it might fit with this newly discovered class of radio transients, which are long period magnetars. So these are pulsars with highly magnetic field that basically live in a part of the pulsar phase space where we don't really expect to find any pulsars. So very interesting. And of course, we perform optical follow-up to get an idea of spectral type of potential optical counterparts and get an idea of whether our source could be in a binary. And I think that's really a place where there's a lot of potential as well in the future when we start to get these optical surveys with very high, cover very large amounts of sky area. We can really benefit from simultaneous observations in the radio and the optical, because of course, ideally we want to see if there's something going on at other wavelengths exactly at the time of this radio flare. However, as I already said, we're not quite there yet. We're not really doing real-time radio transient searches in the image domain yet. So in the time domain, they're a bit closer. So that's where we find the fast radio bursts. But in the image domain, where we look for the slower things like afterglows or this minute sources that show minute duration flares, we're not quite there yet. We're hoping to get a bit closer with LOFAR 2.0. And I think we should definitely be a bit closer at the time of the SKA, because otherwise we will also be drowning in data, similar to what I've heard for the LSST. And yeah, I just want to finish by saying that maybe we can in the future have a radio transient broker. So it's been really interesting to hear about everything that you are already working on, which maybe I will need in the future to do the same thing for radio. So thank you. I'll stop there and I'll take any questions.
Thank you very much, Iris, for a really nice talk.